In this video, we are going to have an introduction to Galois theory. In Hurston book 5.6 is the elements of Galois theory. And actually, Galois theory establishes a one-to-one correspondence between the subgroups of group of automorphisms of an extension field K of a field F and the subfields of K, which means we have already mentioned that K is an extension of F, means K contains F. So you consider the collection, say tau, which is the subfields of K containing F. You are given an extension field K of F, say. You collect all the subfields of K containing F. So you have tau to be that and tau prime to be the subgroups of GKF. GKF is yet to be introduced. So when say at the beginning we will be saying that GKF is the collection of all automorphisms which keeps the automorphisms of K, which keeps the base field element fixed. F is called the base field element, K is extension. So what is GKF? That in a short while we will have. But as for the main aim of this section is concerned, this is what we are going to have. Mainly, we are going to relate the fields. Any subfield is treated as a field. The relation between the field and subgroup treated as a group. So field between a relation between field and groups. Actually speaking, subfields of K containing F, and here subgroups of GKF. What is GKF? It is collection of all automorphisms of K. What is K? K is an extension of F, which leaves the base field element fixed. Right. Now, automorphism of a group we have learnt already. Now here we are having an automorphism of a field K. The same definition holds. You must have automorphism, means domain and codomain should be the same of the function. So if we denote that function to be, say, sigma, then from K to itself, that mapping sigma will be, and you have to have that sigma to be one-to-one onto and homomorphism, ring homomorphism. There is no word called field homomorphism. You have sigma. You are given K to be an extension of F. That means K contains F. And what is sigma? It is an automorphism from K to itself, which means sigma is a mapping from K to itself. Sigma is one-to-one, sigma is onto, and sigma is a homomorphism. So if we have all these three to be true, then you call that sigma to be an automorphism of K. So throughout, see, we are going to just give an introduction. We are not going to go in depth as for the introduction is concerned. So what is that actually we come across repeatedly in this section? So whenever you have, see, you collect all the automorphisms of K, call that group as G. And here you have, see, two people are here. One is collection of subfields of K. The other one, collection of subgroups of GKF. You can imagine this to be the groom's or bride's family, just for comparison, and this to be groom's family, something like that. Not a direct analogy that you have, just to remember that two families that we will be discussing throughout: groom's family one and bride's family. So bride's family, it starts with G, collection of all mappings, okay, which are one-to-one, onto, and homomorphism. See, as for this section is concerned, there will be lot of terminologies and notations that we keep using. So once you understand what is which letter is used to represent what, so if we have the basic idea in that, then following the theory is very simple. So just remember, இது Manamagan family, அது Manamagal family. So like that you remember. So always when we have a person over here, do we have something similar to that over there? That comparison, so that you will know that we need to compare. So here then again the students get confused that what is K and what is KG and all. So there are only two things. One is mapping, the other one scalars. So what you have in this collection, that is in this you have all mappings. In this group, this is what we have taken as Bright's family. Manamahal. And this one is Groom's family, Manamagan. Okay, so we have these two group, these two collection. Um, here K. K தான் பெரியவர் வீட்டுக்கு பெரியவர் வந்து யாருன்னா அந்த K. So K is the first person and that K contains F. So with that only everything starts, right? So K is a field which contains F. So எங்கேருந்து ஆரம்பிக்குதுன்னா K containing F landa we are starting, and what is F? F is the base field. So here, and then it goes, and here you have, or in other words, from K it comes down up to F. So K is an extension of F that is given to you, and then you consider mapping. So how to remember that these are all mappings, and this one is field. So one you fix, the other one will be automatic. That is, you remember like this: mapping. Only two things that throughout that we are going to come across. One is mapping, the other one scalar. These two people only will be ruling the entire section. So one will be mapping, the other one will be scalar. So how to remember that G should consist of all mapping? See here, when you consider this one, you have G. It ends with G, So G means all mappings. What type of mappings? One-to-one, on-to, homomorphism. From where to where? From K to itself. So G is the collection of all automorphisms from K to itself. G is collection of all, not simply mapping. They are just to remember that G stands for what. So for that I just said mapping. But otherwise G is collection of all automorphisms. So sigma from K to K such that sigma is an automorphism. So this collection only we have in G. அதுக்கப்புறம் we can say after a few years that he becomes grandfather and she becomes grandmother, and you have the correspondence. So like that, son, then daughter-in-law, again and some for him, son, daughter-in-law, like that. So you have that G. When you have G, at once what you will talk about KG. When you have G, you can talk about KG. So and then when you have H, you can talk about KH. When you have GKF, you can talk about KGKF. When you have GKT, you can talk about K suffix GKT. So that is how throughout it will go. What it stands for what, and this one stands for what, all that will be explained in the due course. But otherwise the overall picture when you want to have in this section, then this is how it goes. You have mappings one group, and then scalars another group. Mappings, you have it starts with G. Scalars, it starts with K. So corresponding to K you don't have anything. K தான் பெரியவர். So அப்போ G to KG, G to KG in the sense, whenever you have G, you can talk about KG. Whenever you have H, you can talk about KH. Whenever you have GKF, you can talk about KGKF. So whenever you have a group or subgroup or whatever it is, you can talk about K suffix of that. What do they stand for? We will see in the next video. But as of now, just we are giving only an outline of the section. So how many definitions that we are going to have in this section, how many theorems or lemmas that we are going to have, and what is that GKF? We are going to call it as Galois group, when, and what is the use of it. So it is such an introduction that we are going to have in this video. Now, section again, 5.6 elements of Galois theory. So the definitions are nearly 7 definitions that you have. First one is group of automorphism of K. And just now I said that collection of all, the G means mapping. Collection of all automorphisms. So it is G. G is collection of all automorphisms from K to itself. So sigma is an automorphism. Collection of all automorphisms of K. Simply in words you can say, or in notation this is how you denote. So G stands for just automorphisms. And then comes GKF, which is called a group of automorphisms of K relative to F. Group of automorphisms of K. Group of automorphisms of K relative to F. What is it actually? It is all those automorphisms of K. From here it comes. That is why Gx sigma belongs to G we are writing. So GKF is the collection of all automorphisms of K which leaves the base field element fixed. அதாவது Fல இருக்கிற எலிமெண்ட்டை மாத்திரம் ஒன்றும் பண்ணாது, அப்படியே விட்டுரும். Sigma of alpha equals alpha. இந்த sigma Kல உள்ள எலிமெண்ட்ஸ் என்ன பண்ணுங்கிறத பத்தி நம்ம இங்க பேசவே இல்லை. அது என்ன பண்ணணும் இந்த GKFல, அது if it has to be a member means what it should do அப்படின்னா, it should satisfy this condition. The base field element should be left as such. அதாவது ஆல்பாவை ஆல்பாக்கே எடுத்துட்டு போகணும். அந்த மாதிரி இருக்கிற இந்த கலெக்ஷனை தான் நம்ம GKFன்னு சொல்றோம். That is called group of automorphisms of K relative to F. So we can also say in words like this, group of automorphisms of K that leaves the elements of F fixed. So next comes the fixed field of G. We said, there are only 2 people that throughout we will be considering. One is mapping, the other one. Mapping means no ordinary mapping, excepting for the one-to-one correspondence in the last theorem that you have. Otherwise, not just a mapping, it is automorphism of K. So collection of mappings you have and collection of scalars. They satisfy some condition. So because of the condition, they are put in some particular pattern of fields. So which we denote in this case, when I have G, KG. When I have GKF, it will be K suffix GKF, like that. So these are scalars. Idu tata, adu party. So Kg is all those elements, the scalars, such that they are fixed by all the elements of G. See, it may look that both of them are the same. They are not the same. See here, mappings, you collect only the mappings which leave the base field element fixed. Here you collect only scalars which are left fixed by all the automorphisms of K. So it is the scalars which are left as such, scalars which are left as such by all the automorphisms. There all the automorphisms which leaves the base field element fixed. So here scalars, their mappings. Mappings, what does it do? Here scalars, what do? They are left fixed. They are not doing anything. The mappings, for all the mappings, they must be left as such. So you have, this is here for all sigma in G, here for all scalar. So when you have here scalar, remember that you have to have mapping here. When you have mapping here, you have to mention about the scalar. So that is it. So it may look the way in which the condition is written it may tell you that they are the same. They are not the same. Here importance is given to scalars. Here importance is given to as far the condition is concerned. The importance is given to mapping. And here the set collection importance is given to mapping G. It ends with G. So G means you have to have um, um, the mappings only. I mean, in capital G, you have to have mappings only. So, if you have mapping here, they are scalar. If you have scalar here, about mapping, you have to mention. So that is how these two together will go throughout. The both of them will come. So this is called fixed field of G, and this is called a group of automorphisms of K relative to F. Right. Then this definition, that field of rational functions, all those functions of this form f by g where g non-zero, this is called, this what it stands for. When that topic comes, we will have better explanation. Right. As for the introduction is concerned, it is enough we know that what is this notation stands for. It is f of ordinary parenthesis x1 etc xn, which is nothing but the collection of all rational functions, f by g format. Whenever we have f by g, g should not be 0. So this collection is field of rational functions. The proof and all we are not going to have, because somewhat similar to that in section 5.1 itself we have established. So that part we are not going to have, but such an expression is called field of rational functions. And we are going to have those functions which are left as such by certain automorphisms. So what are those rational functions are called? They are called symmetric rational functions. So not all of them will be taken to themselves. I mean, the sense that if you consider, say for example, if you consider just a simple example that we will have. See, when you consider x1 plus x2 plus x3 to be a function of x1, x2, x3, and another you have, say, x1, x2, x3, this to be a function of x1, x2, x3. Now, the sigma stands for permutation. Sigma belongs to Sn, so that means it's a permutation, which means these they'll be introduced as roots, so they can be interchanged, but still the function will remain the same. So such functions are called symmetric rational functions. So here you have all x1, x2, x3. Here the product. There you have the sum. So whether you interchange, I mean, if you interchange any two xi's and xj's, the whole lot will remain the same. So they are called symmetric rational functions. You may think that for all it will be like that. No, it is not so. See, if you consider, say for example, f of x1, x2, x3, I have it as, say, x1 square, x2, something like this. And if I consider g of x1, x2, x3, if you consider this, and that is, say, x1, x2 plus x3 square, something like this. So this divided by this, not equal, this divided by this. So when you interchange these two, say x1 and x2, this becomes x2 square x1. So in the numerator itself we have different functions. So that means there is no need to check in the denominator. When the numerator itself changes, there is no need to talk about any change in the denominator. So they are not called as symmetric rational functions. Only those functions which are left as such by any permutation sigma is called symmetric rational function. Then another definition is normal extension. Just a finite extension of a field f. We know here you have the definition of normal extension K of a field F. So, what is the condition required? You must have K to be a finite extension, and the fixed field of GKF should be F itself. Actually speaking, when you write this definition, this one says that these kgs, what we had here, no, these kgs are subfields of K. They are nothing but the subfields of K. So we have this one KGK, it's a subfield. So F is also a subfield, and any field is a subfield of itself. So this KGKF can be either F or K or any field coming between K and F. So, but KGKF is, I mean, the resultant will be like that. But if I have KGKF to be F, that's one condition, and K should be finite extension of F. So, if you have these two conditions to be true, then you call K to be a normal extension of F. Next, we have the Galois group of a polynomial. See, when we have K to be the splitting field of a polynomial, then the Galois group of the polynomial is given by if K happens to be the splitting field. If K is splitting field of some polynomial, say f of x over f, then GKF, it is nothing but all those mapping G for mapping. G from sigma to sigma, from K to K, such that sigma is an automorphism. So that is your G. But GKF is all those elements which are left as such by all the, I mean, which are all those mappings which leave the base field element fixed. So here mappings that leave the all the elements of F fixed. So um, that is your GKF, that's known already. But when K happens to be splitting field of some polynomial, then the name given to this GKF is Galois group of that particular polynomial. So, so these are the definitions that we come across, of which uh, to prove one major theorem that these notations are very much required. We'll discuss about them again later in one of the videos. And what is normal extension? What is normal extension? So next, how many theorems that we have? So 6 theorems and 3 lemmas. 6 theorem and 3 lemmas that we have in this section. The first theorem tells about the linear independence of automorphisms, sigma 1, sigma 2, and so on, sigma n, b. They are all automorphisms of K. So, what we are trying to prove in the first theorem is that they are all linearly independent. Then, in the second lemma, the fixed field of G is a subfield of K. Fixed field means all will be scalars. So, it will be a subfield of K. So that needs to be established. And then group of automorphisms, next lemma. That is GKF is a subgroup. In short, if you want to say GKF is a subgroup, here KG is a subfield. So these are all section A questions. 2 மார்க்குக்கு கேட்பாங்க. Then the next theorem, the relation between the degree of finite extension and group order. So order of GKF is less than or equal to degree of K over F. And next, we connect elementary symmetric functions to polynomial roots. That comparison that we are going to have, and based on that we have one theorem, that's 5.6.3, which has got some 4 subdivisions. Degree of K over S should be n factorial, and GKS should be equal to Sn, and f of a1 etc. an is S, and the splitting field characterization is given. Now, next theorem is the relationship between degree of normal extension and group order. So, the relationship between the degree of normal extension um, and group order of GKF is uh, less than here it is less than or equal to, but when you have um, the K to be the splitting field. Splitting field means normal splitting field. K splitting field means K is normal. So that will be established in the fifth theorem. That's section C question. This one repeatedly asked question. Um, so here equality. See, we have already that order of GKF to be less than or equal to degree of K over F. But here we are saying that order of GKF should be equal to degree of K over F. So how is it possible whenever you have K to be splitting field of some polynomial, then this can happen, right? So this is the criterion for K to be normal in F. K is normal extension. So K normal means K should be splitting field. Next is the connection between the group theory and field theory, the fundamental theorem of Galois theory. So that is your fundamental theorem of uh, Galois theory. So ultimately, what is Galois group? It is a group of field automorphisms of a field extension K that fix the base field element. So that is our the description of GKF, and we say that it represents the permutations of the roots of a polynomial. It represents the permutation. Now, with an example, this statement will be explained that we will see either in the next class or afterwards. But definitely in the illustration or problems, you will come across such thing. What is Galois group? It is a group of field automorphism functions that map a field to itself, preserving operations. So that is the definition of automorphism that's known to us. So it's a group of field automorphisms of a field extension. So if you take that field extension to be say K, that fixes the base field. So that is your GKF. Repeatedly, we are saying that GKF will consist of only mappings sigma belonging to G such that sigma of alpha equals alpha. Here sigma, when you have, then what is that you can have talk about this. It is all should be from F. So that is your GKF. So that's called once K becomes a splitting field, automatically this one will be called as group called Galois group. Now, what is the need to study this Galois group? You can without solving, you can you need not even touch the equation at once. Once you have the polynomial, there is no need to have whether it has roots or not. By just looking at the degree, we can easily say that roots, every polynomial will have roots. The question is whether you have any formula directly, you can substitute the coefficients and you can get the roots. Whether it is possible means the question is no. That also we are going to address later. So solvability of equations, to know about it, our Galois group, this discussion will be very useful. And then it connects, at the beginning itself it said that it connects fields and groups, and it bridges the gap between the study of fields and groups, the same thing. And next, it is fundamental to mathematics, because as in understanding the deeper concepts in algebra and the number theory, this one is very essential. So um, this is the as far the introduction is concerned. Remember that you have six theorems, two lemmas, and seven definitions. So if we just again go through all the definitions and the results without proof, right now proof is not needed, because in this we haven't proved anything also. So um, this is the what is Galois group that we had, number of theorems, number of definitions, and why we need to study about it. All this that is covered in this introduction to Galois theory. Thank you.